let's now look for another practical example, this time non-linear. And we are going to deal with portfolio optimization. In general, a portfolio optimization problems deal with the problem to get the highest expected return out of a given portfolio of assets. So the problem is to choose the share of the different assets in your portfolio as to maximize the expected returns of your assets while reducing its variance. So you have a return out of your portfolio given by the return of the different assets given their shares, but you also have variance of this return, and you will measure this variance. What gives the variance is the covariance matrix between the different assets. So if two assets go together, take for example stock of gas and stock of another energy product, when one go up, the other one go up as well, and so the covariance is very high, while in other for example gold and stocks on the market stocks, they often go in different directions. So you can put these two assets together in order to reduce the variance of your portfolio. So the objective problem here is to find these shares of this optimal portfolio. And here in this example, again, we're using forest speeches, and this is out of a paper that you can see here. So the model itself is well described in this paper. I'm not going much more than a few sentences out of the model. We'll concentrate on how to solve it in Julia, but the idea is that you can see here this chart, this chart. So you have different, if you measure here the profitability of your portfolio, the expected return and its variance, depending on the different share of your asset, you will have different points here of this feasible set. So you will have different possibilities depending on the share of that you assign to the various assets. And what you will want to have some combination that is in this so-called efficient frontier, because it is efficient in the Pareto sense that you cannot increase the profitability without at the same time increase the variance, or the opposite. You cannot reduce the variance with at the same time lowering the expected profitability. So for sure you will want 1 point on this sentence. You don't want a point here, because a point here is not efficient, because you can increase both profitability and reducing the variance by choosing a better allocation of your portfolio. At this point, you have a set of points, an infinite set of points, and you want to choose one particular point, and which point you will choose depending on the risk aversion characteristic of the portfolio owner. So if you are very risk adverse, you will accept more variance for a higher return. If instead you really are risk averse, you will choose the point at the lower variance. So this is another optimization problem, but we'll see that is non-linear. So the only things that change here is that the solver engine will be IPOPT instead of GLPK. Again, this is about forest speeches, but here we could have put any other kind of assets. So we have 4 speeches, and we measure the profitability in terms of volume of timber produced on average. And these speeches, they have some covariance that has been measured, and depend on how much the ecological conditions are similar. For example, between chêne pedunculate and chêne sessile, sorry, these names are in French, they are much more correlated than with the pinus, that is a coniferous. But really doesn't matter here the specific names of the species. So here is the covariance matrix between the different forest species, and again I'm putting them in terms of a dictionary so that I have it in terms of species 1, species 2, and relative covariance. And for the rest is very similar. So let's go to see this, how before we solve the model with JUMP, let's go to run the same model by simulation. So I'm taking 1000 samples, and I'm just making random shares to see which is the set of possibilities that I have. I forgot here. So here I have a set of 1000 shares. So these are vectors. I'm going to transform these vectors, these 1000 vectors, in probabilities. And to do that, I'm starting to use BetaML, that is a beta machine learning toolkit, where that we'll see during the machine learning part, that has a softmax function. What is a softmax function? Softmax is a function that transform, rescale any array in an array of probabilities that is the sum to 1. This rescale can happen at different level, that is they can be more concentrated or more spread out, these probabilities, and this is controlled by this beta parameter. So at the end, apply the softmax function. I have a matrix of actually I have 1000 vectors where each one is a probability. So here they are all positive, and they all sum to 1. Now, given these shares of my portfolio, let's go into compute which are the scores of this portfolio in terms of the variance and the expected returns. So I'm here creating a matrix, an empty one, and here for each samples I'm computing the variance given by the share of the assets and the covariance, and the expected profitability given the profitability of each species by its share. Okay, so after this one, I can plot it, and the first line I will have the first column. I have the variance, I think. Yes, and the second one I have the expected return, and here it is. So each of these points is the result of one random sample, where I have one random distribution of my assets, and here, so these define the feasible set. That is it. I cannot have something here or something here. I would like to have something, maybe I would like to have something here, very low variance and a very high return. So here is the returns and here is the variance, but it's not possible. The only possible feasible sets is this one. And now we are going to see how can we obtain points that are on these frontier. So this is the efficient frontier, more or less, here. And how can we obtain points on this frontier by using optimization? Let's start by writing the code to write one optimal point, and then we'll transform this one in a function so we can run it, because the different points will be given by different risk aversion coefficients. So we'll make this one as a function, and then we will run with different aversion coefficients. But let's try first with one. So let's call 0.1 our risk aversion coefficient. We call the model portfolio for portfolio optimization, and we see that we use iPopt, a nonlinear solver. We define our variable. Our variable is the share, so for each species, so it will need to be non-negative. And the only constraints that we have here is that the sum for all the species must be equal to 1. The objective function is a minimization. I don't give the details of how we arrive here. It's you find it in the paper if you're interested, but is a minimization function, and you can get it here. It's a quadratic function, and we can print the model. So here is the objective function, and here is the constraints. And the one important thing here is that we need to declare the objective with this NL objective macro, because it is non-linear. Actually, in this case, because it's quadratic, I could have just put it objective without NL. But in general, when you have an objective function that is not linear, you need to use NL objective as well for the constraints. These are linear, but if they would have been non-linear, you would have had to specify as non-linear constraint macro. Let's gonna optimize. You will see here that we have it feasible and locally optimal, because all what iPopt can tell us without other information is that he found an optimal solutions, but it doesn't guarantee us that is a global optimal. But in this case, we know by other information that it is a global optimal. So here is the output of iPopt. It tells us some information about how many variables there are and the steps to reach the optimality. So here we can get the objective value that is not particular of interest in this case. But what we are interested are the optimal shares, and we can print here the share. So here is basically 0, 0, and here basically 74% of Hetre, 25% of Pine Sylvestre, and these are the two shares, the share of the species that optimize the problem. We can compute the variance and the profitability, expected profitability of this specific portfolio. So now we did it for only one point. Let's going to do exactly the same, but we put it in a function, compute optimal portfolio, where we give the species, we give the expected returns for each species, the covariance matrix, and a specific risk aversion coefficient, and it does exactly the same that we did here. But at this point, when we have this as a function, we can have different risk aversion coefficients, and we can get as before the portfolio optimality score. This is an empty matrix, and we can fill this empty matrix with the optimal shares depending on the specific risk aversion coefficient. So here we keep it everything constant. What we change here is just the risk aversion coefficient that we defined in this range here. At this point, you can see that it's very fast. It did optimize all this problem in a fraction of a second, and we print this point, and you can see here in red. So we have points at different level of this efficient frontier here. Now you will say that look a little bit strange here, but the results is really in line because of the scale. It seems a bit strange compared with the chart that you saw earlier. But let's go into use concentrate here around the risk aversion coefficient that define this point here, and you will see that you have a figure that is very close to the theoretical one that I provided earlier. So here again we did it for forest speeches, but it's a very general method to optimize a portfolio of assets when you have a trade-off between the expected returns of the portfolio and its variance. That is a very typical situation.